Okay, here we're going to be traversing a binary search tree, and we're going to try and see the connections between Racket and Java code. Specifically, we're going to write the method height. Okay, and as a reminder, here were the helper functions that we were using in Racket, and then here was the structure that we had created for a binary search tree, and then our binary search tree nodes, or the BST nodes. So we previously wrote height in Racket, and height was working with a single tree, and so this is a thing that's a little bit different between the Racket and Java versions. So here we could get an empty tree, and then we could call height on the left and right tree. You'll see in the diagram on the previous slide, it's really in Java the BST node that has access to that left and right tree. The binary search tree, that root node, just gets us to that first BST node. But you can think of the Racket one as made up of only BST nodes. Okay, so your task is to try and write height in Java, and you might pause on this screen so you can see the height in Racket and the structure of the binary search tree and BST node. So I'll assume that you've paused the video and then I'll go ahead and live code it. Okay, so I have a stub right now for get height. It's going to return an int, and right now I just have it always returning a 0. It's a little tricky because to replicate what we had in Racket, I really want to be working with BST nodes. So I'm actually going to make a private version of this method. It's going to be private int. I'll still call it get height, but this time I'm going to take in a BST node, and I'll call that current node. Okay, and it doesn't compile right now because I need to make sure it returns something. Okay, so I'm going to work with this private get height method so that it can work more similarly to how I was able to write it in Racket. I'm going to paste in the body from the Racket so that I can use it as a reference. Okay, there we go. So my first thing is, what will it look like here when I should return -1? Well, if I get past a current node that's null, then I could think about returning -1. So I could say if current node is equal to null, I'll return -1. And I'll make sure I've still got a return type or return value in there. Once we've got this empty case in there, we can start thinking about how it relates to the public method. So here you can imagine that I call get height with this dot root node. So imagine I have an empty tree, so this dot root node is null. Then I'm going to call get height. Whatever root node is, which was null, will be our current node. So current node will be null and will return -1. Okay, so I know even right now, I can tell that my code's going to work for the case of an empty tree. Let's add in this second piece where we need to call height on both the left and right tree, calculate the max, and then add 1. So I can get the height of the left. I'll call that left height. That's going to be the current node dot left tree dot. So that's the node, but instead of saying dot get height or whatever, for this private method, that's actually going to be the argument to get height. So I'm going to pass my left subtree to the recursive call of the method get height. Just like here, I pass my left tree to the recursive call of height in Racket. Sorry to spell height incorrectly. Okay, I'm going to do the same thing for the right height. I'm going to call get height on the current node's right tree. Now that I've got both of those, I can add 1 to the max of those two values. And to do math, I can do math.max of left height and right height. So we already talked through when root node was null, but imagine root node wasn't null. I would call height, get height on its left tree and its right tree. I would take the max of those two things and then add 1. So that worked just like we saw in Racket. Let's bounce back to the slides to compare them. And again here, this structure of two methods is really important. And we needed this helper function to traverse the tree like we did in Racket. Because instead of working with a BST or with a binary search tree that all it has is a root node, we wanted to work with the actual BST nodes. So we can see the comparison side by side of the Racket on the top and the Java on the bottom. Or even here, instead of creating those variables for left height and right height, you could see I could put it in line, and the Racket code is shown just below. Another thing I did in this version is I named that private helper method something different. So I called it height from node, just to draw our attention to the fact that we're not calling our original height method again. Did you notice in the code that I wrote in the previous example here that I didn't use this dot to call my methods? They were being called on the BST object, the binary search tree object, and not a BST node. The BST node is the input, that local variable, or that argument is helping us keep track of where in the tree we are. But actually, all of these methods are getting called on a binary search tree object. So inside height from node, we never use it, but we could access this .root node. And I think that part can be a little bit tricky. So make sure that you review this to understand why do we have the two methods and how this second method that keeps track of the current BST node helps us traverse the tree recursively.